Hey y'all, in this video we're going to talk about section 2.3, the polynomial functions and modeling. So we're going to talk about a couple different types of functions and just a bunch of different ideas with the functions. A lot of it is stuff you would have learned back in Algebra 2, however, you may have not remember, so we're just going to run through everything real quick just so you have it in your brain, okay? So cubic functions, they've got a degree of 3. Quartic have a degree of 4. You can keep going up and up the list, but those are the two most common ones that we'll be adding to our list of polynomial functions. Now, standard form is whenever you write your polynomial with your terms with like descending degree order. So you would start with the highest degree and then work your way down. We have a fun little theorem here, which is just, it doesn't really have a technical name, so we're just going to call it 2.1. But it talks about the number of zeros of a function, the extrema, your points of inflection. So a polynomial function of degree n, as long as n is greater than or equal to 2, right, then we're able to know these things, right? So as long as your n is greater than or equal to 2, has at most n zeros. So if my function has a degree of 3, then it has at most 3 zeros, at most 3 places where it would hit the x-axis. Okay, it could hit less, but the maximum amount of times it could hit the x-axis would be the number of that degree. All right, n minus 1 extrema. So say that my highest degree was a 3, right? It would have at most 2 potential extremas. It doesn't mean that there are 2, but there are a possible amount of 2, okay, at most. N minus 2 points of inflection. So let's talk about that degree of 3 again. Well, 3 minus 2 would tell you that there was at most 1 point of inflection. It doesn't guarantee that there is any, but there is at most that many points of inflection. Say that you had a degree of 6. 6 minus 2 would be 4, at most 4 points of inflection. Okay, so that's just a cool little trick to kind of help you with visualizing a graph, even if you don't know much else about it. If you didn't have a graphing calculator handy, which on our AP test, you don't get a graphing calculator for about half of it, right? So we got to be able to know features of functions without one as well. Okay, now here's another thing that's really handy to give us a nice little picture of what our graphs look like. This is talking about end behavior. Okay, now you should have gone through something similar to this in Algebra 2. I'm not sure if you guys used the limit notation or not. Let me zoom in a little bit more so you've got all this a little bit easier to see. But we're just basing everything off of the leading term for your polynomial. So you make sure you look at the highest degree, and we're going to use that term, the whole thing, the coefficient and the exponent. We're going to use both of those things to be able to determine what is happening on the ends of our graph. So the theorem we're just talking about basically talks about the middle of your graph. Where does it hit the x-axis, or how many places, local extremas, how many times does it turn, right? Points of inflection. That's all talking about the middle of your graph. However, when we want to talk about the ends of your graph, that is something we're just going to look at the leading coefficient and be able to tell what shape this thing kind of generally has. Okay, so whatever your exponent is, if it's odd or if it's even, it's going to have these different behaviors, right? The leading coefficient, if it's positive or negative, it's going to have these different behaviors. So what I want you to focus on just real quick is if it is odd, okay, I want you to look at these ends. These go in different directions. On one side, they're going up. On the other side, they're going down. Okay, look at my other one that's odd. Same thing. One side it goes up, the other side it goes down. Whereas even, they're going the same direction. Okay, they either both go up or they both go down. So that's the first thing I want you to notice. Okay, look at odd or even exponent, and it tells you, do the ends even go in the same direction, or do they go in different ones? Okay, now here's the other thing I want you to look at. Look at what's going on when the leading coefficient is positive. Do you see how the right side of it is going up in both of those cases? Whereas when the leading coefficient is negative, do you see the right side is going down for both of those? That's a really easy way to visualize this graph. If I know that the right side is going up and it was odd, that means that the ends are different. So if the right side is going up, the left side would be going down. Whereas if I'm looking at it being positive and even, positive shows me that the right side's going up. Even means both sides go the same direction. So I know that that's what's going on the ends. So you can use that to help you out with following through and making sure you know what's going on the ends, just even as a picture. But we like to also be able to answer these using limit notation. So let's make sure that we can break down that. I'm going to zoom in just a little bit more so we can see this a little better, okay, for each one of these. And really what I want you to focus on when it comes to this limit notation is what is happening visually, and we can put that in this notation. So just look at this first limit, okay? You see how it says the limit as x approaches negative infinity. What that means is as I'm looking on the left side of my graph, okay, as it approaches negative infinity, this is the limit that's talking about the left side. Well, on the left side, do you see how this graph was going down? As that graph was going down on the left, or going to the left, it was also going down, which means that my y's approach negative infinity. So as x approaches negative infinity, y also did. Okay? As it goes to the left, it was going down. Then over here, as x approaches positive infinity, what's going on with my y's? They're going up. So as x goes to the right, the graph is going up. Right? As we go to the right, it's also going up. That's how I'm reading it. Look at the next one. This one, they were both going the same direction. They were both going positive. Well, look here. On the left side, as x goes to negative infinity, right, then my y's go to positive infinity. As it goes to the left, my graph is going up. That's how I read it. On the other side, it says, as x goes towards infinity, as we go towards the right side, my function is going towards positive infinity. It is going up. Okay, so those limits, that's how we read them. I'll run through these real quick. We've got here, as my x approaches negative infinity, so as it's going to the left, my y's are going up, so it's going towards positive infinity. Going down here, as my x goes towards positive infinity, so as it goes to the right, my y's approach negative infinity, meaning that they go down. Okay. As my x approaches negative infinity, as it goes to the left, my y's approach negative infinity, they go down. As it goes to the left, it's going down. And the last one over here, as my x goes to positive infinity, as I'm going to the right, what happens in my graph? Well, it goes down towards negative infinity. Okay, so limits are just that, trying to see what does something approach infinitely. Okay. All right, now look here. It says, just some little tips and tricks to help you remember. So if it's positive, the right side's going to go up. If it is negative, the right side's going to go down. Okay. If it's even, both sides are going to match. If it's odd, they're going to be different. Okay. So just use those to help you with going through these types of problems. All right. We're going to do an example down here. And all they're asking is to describe the extrema, the zeros, and the end behavior. Guys, we do not need a graphing calculator to answer this kind of a question. All right. If you had a graphing calculator, sure, you could throw that in there, but honestly, it's a waste of time. It is so much faster if we're able to do it by hand. So that's what I'm going to go through. We're going to look here at letter A. All right. Now, the first thing I want to pay attention to is what is my leading term? Well, I'm going to look through, make sure it's in standard form first, which it is. That highest degree is a 3, and that one's listed first. All of the exponents are written in descending order. So that tells me my leading term, that's my leading. Okay, that is x cubed. Well, I see that this is positive. I also see that the exponent is odd. Okay, so when they talk about listing my extrema, listing my number of zeros, and listing my end behavior, guys, they didn't say to actually find the zeros. They said to describe. right? So what we know from our theorem is that the number of zeros will match their exponent. So if I say my number of zeros, there's going to be 3 at most. Okay? We also could look at this and say, okay, what about my extrema? Well, extrema, didn't leave myself a lot of room, did I? My extrema will be n minus 1 as my potential extrema. Well, my exponent there is a 3. 3 minus 1 tells me that there's 2 at most. Extrema. Okay? When we talk about my, that didn't ask about points of inflection. We could have given that as well. Okay, now they said we want to describe the end behavior. Well, this is where I'm going to follow. If my leading term is positive and odd, odd tells me that the sides are going to go different directions, and positive tells me that the right side is going to go up. So what I'm thinking is the right side's going to go up. Odd tells me that the other side's going to go down. So that's what I'm picturing. I don't know necessarily what's going on in the middle. We could kind of graph the whole thing, but what I know is that on the right side it's going up, on the left side it's going down. So I'm going to list out my limits. Okay, for my left side, I would say my limit as x approaches negative infinity for my function. As my graph goes to the left, it's going down, which means it's going towards negative infinity. Okay, as my x goes towards positive infinity, as we go to the right, my graph was going up. So that tells me my y's are approaching positive infinity. That's my end behavior. Let's do the same type of thing for part B. Okay, now they ask us for the zeros. Now again, we want to make sure we know where our leading term is so that we have our highest exponent. This is in standard form again, so that's nice. My leading term, right? That's this guy, the 2x to the 4th. Okay, so that tells me positive, right? This guy tells me even. So knowing those things, I'm able to answer my questions pretty easily. Now remember my zeros, I have the potential for the same number of zeros as my highest exponent. So I have a potential, we're going to say at most 4. My extrema, if I could spell, it would be n minus 1 as my possible amount. So my exponent is a 4. 4 minus 1 is 3. So at most 3. And then let's talk about our end behavior. Okay, because it's positive and because it's even, I should know exactly what's going on. So positive means my right side is going up. Even means that they are matching. So they're both going to be going up. When I list out my limits, I'm going to have limit as x goes to the left, negative infinity. As x goes to the left, my graph is going up. So y's are approaching positive infinity. Whereas as x approaches positive infinity, as we go to the right, my graph is going up as well. So also going towards positive infinity. Okay? So that's how we answer those questions, with just trying to describe those. And it gives me a good picture as to what's going on, at least on the ends. And we can kind of visualize a little bit of what's going on in the middle. The rest of this lesson, we're going to continue seeing a lot of that, where we can see what's going on in the middle of the function. Okay, so let's see. Maybe we can get one more example in here. Okay, let's talk about multiplicity. All right, so multiplicity, if we can get this one more example in here for this video, and then I'll do another video with the rest of it. So what can happen sometimes is you can have a zero kind of repeat itself. And that is honestly fairly common. If a zero repeats itself, then we say that it has a multiplicity of whatever that is. Okay, so you'll see, like, if multiplicity m is greater than or equal to 2, then the zero has a repeated 0. When you have a 0 repeat an odd number of times, then the graph will cross at that 0. It will actually cross the x-axis. Whereas if it has an even multiplicity, it's actually going to kind of bounce off of that 0 rather than cross it. So you'll see it says the graph is tangent to the x-axis, meaning it's not actually going to cross it. It will hit it, but then bounce right back away and not cross through. So we're going to look at another example here. Now this one says to state the degree and list the zeros, state the multiplicity and whether the graph crosses or not at that intercept, and sketch the graph. Guys, I'm going to do this whole thing without a calculator. You do not need one for a question like this. Okay, so I'm going to show you what we would do. All right. So on A, right, we're going to take this, and I'm going to start by figuring out where these zeros are, because on this one, we can totally do that. They said state the degree and list the zeros. They didn't ask how many zeros are there. They want us to actually list them all, which means I would need to find them. And in order to do that, if I can factor it, it's going to make things a whole lot easier. Well, out of these two terms, I can factor out an x squared, and that would leave me x squared minus 25. In the parentheses now, I have a difference of squares, which factors really pretty. It would be x plus 5 and x minus 5. Okay, so just being able to factor like this, I'm able to see all of my zeros. Here I can see that x would be 0. I could have negative 5 or positive 5. Okay, the way I find those is I think of, if I set this equation equal to 0, what are the x values? So this gives me the zeros. Okay, we have the 0, 0, 0. We have the 0, negative 5, 0. And we have positive 5, 0. Now, there's one of these that actually repeated itself. You see how x was being squared over here? So that 0, that has a multiplicity of 2, whereas the other ones only happen once. So I'm going to say multiplicity of 1, multiplicity of 1. I know whether it bounces or not, or crosses, based off of if that multiplicity is odd or even. So because this one is even, I know that it's going to bounce. Because this is odd, I know it's going to cross. Okay? So when it goes to sketching, what else did they want? I missed one. Oh, they wanted us to state the degree. The degree on this one, the highest degree was a 4. So I missed writing that one down, but that's what that was. Okay, the degree, the zeros, state the multiplicity, and whether it crosses. Okay, so I've done all that. The last thing I have left to do is to sketch this graph. So let's do that. All right, I don't need a lot of space. I'm not looking at making this thing perfect. What I am going to do is find where my zeros are. I know I've got one at 0, 0. I have one at negative 5, 2, 3, 4, 5. And I have one at positive 5. Okay. And then I know that based off of the leading term, I know that it's going to have that behavior where the right side is going up because it's positive, and because the exponent is even, the two sides are going to match. So I know that on this side, this is going to be going up. I also know at this 0 that it's going to actually cross my x-axis. So it's going to dip down here. Now, I don't know how low this is going to go without actually doing more math, but I can get a little rough sketch of this. So I know it's going to dip below. Now, remember how we said at 0, 0, it's supposed to bounce. So when this comes back up, it's not going to actually cross at this 0. It's going to bounce back under, and it'll come back, and then it will eventually cross at that other 0. Now, again, I don't exactly know how low this thing is going to go there. I don't know how sharp that curve will be. But this gives us a little rough sketch of being able to see what the graph looks like, and I don't need a calculator. That's what I can visualize in my head when I see that equation, okay? And the more you do this, the more natural that will come to you. All right, let's do the other one. I'm going to pick a different color just so that these don't run together too much. All right, so on this next one, they went ahead and factored it for me, which was super duper nice of them. We have right here where I can see there's going to be a 0 at x equals positive 3. and there's going to be one where x equals a -5. Let's go ahead and state the degree so I don't forget to. Now, I don't see degrees written on those x's, but I do see it on those binomials. And that is going to cause this to be an x squared. This is going to cause this one to be an x cubed. Those two eventually get multiplied. This is going to be a degree of 5 if it got all the way FOILed out. Okay? So I don't have to do all of that. I just know that that's what it would result in. So I know it's a degree of 5. Just add the exponents. That's your shortcut. Okay, now to get my zeros, I'm just going to think of setting each of these equal to 0. Basically, take the opposite of what's inside. So my zeros would be at positive 3, 0, and at the opposite of this, -5, 0. Okay, now these do both repeat. So they both have a multiplicity. Let's see, the first one had a multiplicity of 2, and the second one has a multiplicity of 3. One of those is going to bounce, the even one does, whereas the odd one is going to cross. Okay? I also know if I were to multiply this whole thing out, that leading coefficient, not only is it going to have a degree of 5, but it's also going to be positive because this is positive, positive, positive. Okay, I don't have anything that would cause my leading coefficient to be negative. So I'm thinking of, like, graphically, what's that going to look like? I have an odd degree, and I know that it's going to be a positive leading coefficient. So on the right, it's going to go up, but because it's an odd degree, the left is going to go down. So I know it's going to look something like that when I graph it. I'm going to go ahead and graph this guy. We're going to have a 0 at positive 3, 1, 2, 3. And then over here at -1, 2, 3, 4, 5. Again, I don't know how high up this thing is going to go. If it was in standard form, I would be able to see very easily where it would cross the y-axis. It's going to be a pretty large number, so I'm not even going to bother with that right now. What I think is more important is us seeing that in behavior. So we know on the right, this thing is going to go up for forever. Now, at the 3, 0, it's not supposed to cross here. It's supposed to bounce. So it's going to go back up, but then it is supposed to cross at this other one and then go down for the rest of its life. Again, I don't know exactly how high up this thing is going to go. Most likely it's going to go up way, way, way higher than what that looks like. But at least this gives me a somewhat picture of it. And we could always find out more details if we needed to later. Okay? So that is going to be it for this video. We're going to split this into 2 parts. This is going to be part A for this lesson. Definitely make sure you stick around for part B. All right. I will see y'all in the next one. Bye.